MacTech since 1984.
You're, by the way, the most important people to us because you talk about machines and you talk to a lot of people and your friends are maybe in similar businesses that you're in. So it's real important that you're satisfied and happy with our product line. So Aaron Burka, who's your instructor today, has been with me for how many years, Aaron? 12. So I'm the oldest guy in the company. I think Aaron's the second oldest. Is that true? But Aaron is a professional press brake trainer, operator. He does most of our installation. He trains our new technicians. He's our go-to guy. He's very knowledgeable. And so he put this agenda together for you guys today. It's a fluid agenda. I think we should kind of go through it fairly quick so you can spend more time on the machine, on the controls. I imagine if you guys, the theory of bending is, pretty important. And there's also some really good online books from the FMA and the Fabricator magazine, the FMA. There's a lot of things in there. There's a lot of math to it. Most of the modern controls do it for you. It's kind of nice to know the underlying stuff to it. So Aaron will go through this basic one-on-one press brake thing, and then I think that we should, if we can accomplish this by lunch, then I think our afternoon should be just on the machine. We have some sample parts, so I think it's a good idea to make a bad part, correct the part, make a part on the left side, the right side, the kind of things that Aaron does on a daily basis when he installs a machine. So since we have a fairly good-sized group, we can split up in two groups. Like Ken can take one machine, Aaron can take the other. We have Sibilec controllers. Does anybody have Sibilec controllers? And we have two Delem controllers out there. That's probably what most of you have. And we even have an old Herco in the corner if you guys wanted to touch it. But in any event, thanks for coming. These are your folders to keep and your MacTech portfolios and various other things that are on the table. And if there's anything you need throughout the day, let me know. Mi casa, su casa. And appreciate it once again for you coming up to MacTech today. You're welcome. Anybody's going to Summerfest, you're welcome to park in my lot anytime. Thank you.
All right, as Mike said, I'm Aaron Burga. I've been doing this for 20-some years. Out of the Navy, or out of high school, went to the Navy for 6 years. Then I got wrangled into work for Cincinnati Incorporated for 5 years. They taught me. They used to have a very good training course for new technicians. They taught me the basics, and then I've learned the rest over the past many years. I've worked on. If you see a press brake controller, I probably know how to program. That's all I've done. 99% of my jobs for the past 20 plus years have been working on a press brake. It didn't matter who made it, didn't matter what controller it was, I figured it out. When it comes to press brakes, I know I guess there's there are still some companies still using mechanical press brakes. Hopefully none of you guys have mechanical press brakes anymore. They're all gone, been scrapped in. And so you guys all have Ermaksan and Delems, is that what I'm understanding? Don't. Okay, whatever you guys do. I guess, so you guys are from, okay. Both you guys? Yeah. Okay. You guys are from? Everyone? Okay. Right, that's great. You
Consolidated Knowledge, Grand Rapids, Michigan.
Okay. You guys are MBA. You guys are from?
Brennan, Jerry Brennan, Kieran Walton, J.M. Brennan.
Oh, okay. All right. Okay. So yes. So once done. So that's what we're going to covering most of what we're doing before. So my next question is, I need to know. So you guys run a press brake currently?
Yeah.
No. Okay. Have you run a press brake before? Okay. You guys, you're currently running it. Running press brakes.
Yeah.
So I need to know if I need to go all. So the guy used to work here, Alex, for how many years? He and I always joke whenever we go in for cleaning out press brake, we want to do press brake 101. So that's just what we call it.
Yeah.
Because we never know going in to install a machine, whether we're dealing with an operator who's been running press brake for 20 years or who doesn't know what press brake is. That's where the mystery comes in, and that's what I'm trying to figure out now, is where I need to, how basic I need to be or how advanced I can.
Start from.
Right. So it sounds like all you guys at least know what a press brake is. So that's a bonus. Because again, it's when I first heard this, I had no idea what a press brake was. I was already hired to tell you were on a press brake. What's a press brake? So you don't need to go into types of press brakes. You guys all have hydraulic press brakes. No mechanical, so I'm not worried about that. Hopefully, you never have to deal with mechanical press brake. They are terrifying. Types of bending. So, what you guys mostly do on your press brakes is air bend. Probably mostly 90-degree bends. On the Delem controllers and most press brake controllers, the controller looks at a flat piece of steel as 180 degrees. And where I see a lot of confusion is when you have a part that is bent at about that angle, depending on who you ask, some may say it's a 45, some may say it's a 135. If you look on a protractor and you set it to 45 degrees, depending if you're looking at this side or this side, it could be either 135 or 45. That's included and excluded angle. Almost all modern press brakes deal with 180 degree flat and this being the 135. Now, the vast majority of operators I deal with who've never run a press brake before, when they look at that, well, that's 45 degrees. Well, in your everyday work, that's what most people do. They say, yeah, well, that's 45 degrees. In the press brake world, that is 135. And it makes a huge difference, especially when you get down to 90 degrees. Because when you're measuring that part at 90 degrees, you have either 91 or 89. And that makes all the difference. You make the correction is knowing which side of 90 you are on. And always remember, if it's greater than 90, you're open, it's positive. If it's less than 90, then you're 89, 80, 85, whatever. And that's where I see the biggest trip up of operators when they get right around that 90 degrees, whether they're open or over. If you do make that mistake, it's not unrecoverable. It's just now you're going to make a worse part than you did the first time. That's controller. That controller is like any computer in the world. The better information you put into it, the better your results are going to be. So I always recommend if you run a press brake and you don't have a set of calipers and a protractor, then you're going to have problems. I see operators all the time. They don't have a caliper. Whatever the sheet comes out, it's just thickness. Well, I don't know if you've ever white material. It varies greatly. It's because it's 16 gauge doesn't mean it's 059. It could be 052, it could be 059, it could be 063. On a standard press brake, if you have the nominal setup, like 16 gauge, 3 thousandths is the degree. So if you've got one sheet that's 6 thousandths different than the last sheet, that's 2 degrees difference from part to part. So that's where when I go and write a program, I always like my material. Because again, the better information I put into that core to begin with, the better my results are going to be. Now the 3 thousandths per degree, once you get into thicker materials and bigger dies, that number kind of goes out the window. But on your nominal 18 gauge, 20 gauge, 16 gauge, 14 gauge, and if you're using the right V die for that material, that's pretty much standard industry, about 3,000 per degree. Which we can get into that. V die. So on thinner materials, again, with 18, 16 gauge, that area, you want your V die to be 8 times as wide as your material thickness. So if you're doing 10 gauge,
Yeah, it would be an 1/8 inch.
right. So if you're doing 1/8 inch, then you need what?
1.3. The die.
No, not for 1/8 inch. It'd be 875 or thereabouts. Anyway, right. So your V opening should be 8 times the material thickness. You can go smaller. Smaller you go, the more your tonnage goes up. That's where you have to start taking into consideration what your ratings are on your tooling. Most modern press brake tooling has ratings on it. If it does not, figures as a safety. If most standard punches, just straight up and down punches and dives, are rated at 30 tons per foot. Now, the one quirk you'll find on Delem controllers is, for whatever reason, they do their ratings in tons per inch. The only one that does it that. Everybody else is tons per foot. But Delem is tons per inch. So then you have to take whatever your rating for your tons per foot is, divided by 12 inches, that gives you your rating for your tool. And most modern controllers have that you get programmed, and it will give you a warning if you go over that rating. If you do go over that rating, that's when you should stop, figure out why you're over that rating. Is it because you've got too thick material for the V-die you selected, which you will get put into that corner all the time by engineers because they invariably will tell you, I want this thick material with this flange, quarter-inch material with the flange this long. Well, you can't do that. You can try, but something's going to give somewhere. And that's where the back and forth between you guys, knowing what the machine limitations are, what the tools limitations are, material limitations are, going back to the engineers and say, look, someone's going to get hurt if we keep doing this. And I see it all the time, where these operators are sitting there bending parts with material that's way too thick and way too small enough. But that's what the engineers want, so then the guys go into it. And eventually blow it up. And someone gets hurt, and no one ever brings it up. Hey, this isn't safe. So anytime you get a warning on that controller saying that the force is greater than die resistance or punch resistance, figure out why. Is it because it's not programmed correctly? Or is it because you're actually putting stress and putting yourself in danger on that tool? Because that's what the engineer does. Sorry, I soapboxed a little bit there. It just drives me insane. I walk into shops all the time and see guys putting themselves in danger because that's what the company wants. Well, I want you to keep your fingers and your toes and everything else. So back to does anyone here do coining anymore? I don't imagine doing. So back when mechanical press brakes were released, there was no accuracy to press brakes. They were all just mechanical. They got it close, and everybody coined, meaning you had a 90-degree punch and a 90-degree die, stuck material in there, and you brought it down to it, forced that material down into that bottom die, and literally deformed the material into the tool. It used 3 to 4 times the tonnage as air bending does. It was very hard on machines, very hard on tooling, etc. But back when it was mechanical press brakes, mechanical press brakes aren't exactly the most accurate thing. That was how they got around the accuracy problems on old press brakes. Well, nowadays we have accurate press brakes. So, what's everybody airbends? The only ones that don't airbend are, again, going back to engineers. Engineers want this nice, really tight corner on their parts. The only way to get that is to point it, bottom it, whatever. So that's, again, goes back to the argument between the press brake operators and the electric engineers' desire. I've seen more and more companies getting away from that. They've slowly learned that destroying their machines and destroying their tooling every 2 years isn't a good way of going about things. So everybody's much more into airbending now. Most tooling anymore is 88 to 85 degrees. If it's my world, everyone would have 30-degree tooling. 30-degree tooling, I can do anything. I can make any angle I want up to 30 degrees. If I get 85s, well, I can only go to 85. If I need to way over a minute part, I can't do it on that tool. The drawback there is you're limited on tons. The narrower that angle gets on the tooling, the lower its tonnage rating is. So it depends on your materials, how thick you're bending. Coining, right? So coining and bottoming, which a lot of people think of the same thing. They're not. Coining is literally coming down, hitting that part, and deforming that part, and you actually see on the part itself, in that corner will be deformed. In that corner will actually be, the metal will be shrunken and thinner in that area where it was bent, which makes for a really nice corner, but it puts a ton, literally tons of stress on tooling, parts, machine, everything. Bottoming is where you come down, you hit it with some tonnage. It doesn't actually deform the material that badly, but still gives you a 90. Problem with bottoming is it goes back to once this piece changes thickness to this piece, then you're all over the place. Again, that's why most people go into air bending. Most press brakes nowadays are accurate enough to go to repeat 4 10,000ths of it. They go to that same spot every time. So assuming your material thickness stays the same, and your grain stays the same, and all the other variables, you're very consistent working. So that's what everybody's doing for the most part is air bending now. So more tooling information. So all you guys, I imagine, have American style tooling. There's American style tooling, there's European style tooling, which I don't know if it really matters here in this conversation, but just briefly. In the end, it all matters on how the punch attaches to the machine. On most of our machines we bring in, the bottom die rail can accommodate both European and American. American tooling has a 1/2-inch tang on the bottom of the tool. This is down in a groove on the bed. European tooling is 60 millimeters wide and fits in the thread on the bottom. On top, however, there's either the center line tang, like on American, where you can rotate that punch around either way on our punch hole, or there's European, which actually clamps in the front, and the center line pressure. So on American, your pressure's on the shoulder. That center line tang is supported the machine. It doesn't actually receive any touch. All your pressure's on the outside shoulder. On European, the tang is on the front, or if you have the right punch order, on the back, and all your force is directly in the center. At the end of the day, it doesn't matter which one you use. They make the same parts. It just matters how it attaches to the machine. The reason I bring all this up, I was in a shop a month ago, and they were running while they were having such bad deflection of their punch as they were bending parts. Well, they had a European style punch in American style punch holders. It doesn't line up at all. So, of course, as they're bending it, it's coming down, and their punch is literally deflecting to the side, which was remarkably unsafe. I mean, they're trying to snap the tool off. Right. So, and they had no idea. They had no idea. Not a clue that they were doing it. So, that's I've been keeping an eye on. Again, a lot. My biggest thing I want you to take home from all this is be safe. Press brakes, on every normal day, you run them, they're no big deal. But if you aren't paying attention, things can go wrong very, very quickly. It's a lot of force in that machine. It's a lot of weight there, a lot of pressure. Pay attention. Having the right tools to the program you selected. If you go and you're running a program that you ran 3 years ago, double check your tooling a bit. One of the big things I do, if I'm unsure about what I'm doing, and that I've got the right tools, because especially if you're running programs from a while back, you don't know if someone's modified that tooling. You don't know what you assume that tooling's the same, but there's no way of knowing it. What I typically do when I'm in that situation, or if I just program new tooling or add a new tooling or whatever, is when I write a program, I'll go and I'll write just a scrap program, and this goes back to the whole 180 degrees. I'll write a program for 180 degrees. Then, because the machine thinks that's a flat piece of steel, right? So if I write a program for 180 degrees, I go cycle, punch, come down, just touch that material, and go back up. Then I at least know all my tooling heights are correct. Then I still have V openings and other things that can be modified, which that's the biggest one people modify is the V opening, so that way they can get different results. But if you get your heights right, at least then you know you're in the ballpark, and you're most likely not going to tear anything. But again, anytime I program tooling, the first thing I do, 180. Make sure it comes down and touches that material. If it comes down and doesn't get close to material, then I know either I programmed something wrong or the machine's not right. Is it time consuming? A little bit, but I'd rather take that extra little bit of time and make sure that what I've got in the machine is what I think it is. then you can go and do your 90 and your 135. So on press brake, and this is pretty much universal. It varies a little bit when you get to the back gauge, but on pretty much any press brake, the ram is the y-axis. And you notice on ours and yours guys should, they'll have Y1 on the left-hand side, Y2 on the right-hand side. That gets important when you start dealing with the longer parts and you've got to make individual corrections for each side. Because I don't care how well the machine's tuned in, how well it's dialed in, how much it's been recalibrated. When you go to longer parts, odds are you're going to have some variance from one and the other. Just because of steel, because of whatever. So that's where it's going to come in. It's be important knowing, keeping track of which side's Y1, which side's Y2. Because you have to put a correction in for the Y1 side and the Y2 side. And I'll show you guys later on. There's actually an extra page in this controller that was added recently. I don't know if it's on your guys' controller. It may be there, it may not. We can always kind of do a software update if you want. There's actually a page a little bit deeper in the controller where you go, you tell it what angle you measured on the left side, what angle you measured in the middle, and what angle you measured on the right side. So if you actually have automated crowning on your machine, another option, it will take all that into account and do a better calculation for you to get you a better part. For the most part, you guys are just doing Y1, Y2. You're not getting into the whole free correction. So anyway, Y is your back gauge, or your ram, sorry. X is your back gauge moving in and out. Every machine that we have has Y and X. Then we get into more options. Again, I'm not sure what all you guys have as far as options. I imagine most of you guys are Y, X, and R. So X is your back gauge moving in and out. R is your back gauge moving up and down. And then if you have Z, that is your fingers side to side. So you have Z1, it follows the same as Y1, Y2, Z1, Z2. If you have real fancy back gauge and you have X1, X2, R1, R2, and you go on further. So all those have been your programs. I'm sure, again, if you guys run the brakes, you know most of this stuff. Just trying to cover all my bases. Well, and if some of you guys have crowning too, I might. Crowning. So, on a press brake, all of your strength on that machine is all the way over the Y1 side and the Y2 side, out where the frame is. That's where the strength is. In the middle is where the weakness is. Where you bend every day in the middle of that machine is the weakest point of that machine. As you get into thicker materials, heavier materials, the center of that machine will deflect. And it will actually bow. The ram will bow up, even though it's a great big chunk of steel, trust me, it will bow up and the bed will bow down. So if you have crowning, whether it be automatic or manual, there's a wedge system in that bed that actually puts a counter action to that. It puts a bow up in the bed, counteract that bend down that happens when you bend the part. So that ideally, when you bend the part, that crowning takes into account the deflection in the ram and the bed of that machine. Now, does it deflect a whole lot? No, it's a few thousandths. Well, that goes back to 3/1000ths of a degree. So that bed and ram altogether deflect 1.5. There's 3/1000ths. Now you're going to be a degree under in the center versus on the end. So that's what crowning is for. If you're not crowning, then you do a lot of shimming. Before crowning became actually affordable and more popular, it was time cards and tape measures and rulers and whatever. You see all kinds of crap to get a 90-degree bend all the way across. And the operator spent hours getting all that dialed in, shimming here, dialing in here, everything. So on our machines, and I'll get into this too later on. So if you have crowning, be thankful. Because again, the old school guys don't like you having crowning because they didn't have crowning and they had to do all the shimming and all the screwing.
I still work with that.
Huh?
I would have a machine like that. I still work with.
Right. Now also on these machines, if you're using the factory punch roll, you'll notice there is a there is a wedge system built into those punch rolls. to give you more adjustability. What I've found, and maybe you guys have, maybe you haven't, but on most Ermaksan have crowning systems. There'll be spots where it's a little bit soft, where it doesn't quite, you'll have 90, 99, but right you have like 99 in this one little spot. And there's wedges in those punch holes that typically they are either set to the middle or the middle. Depends on who assembled the machine, whether I installed it, whether I was here or not. But as you move those wedges over, it makes that point of that machine bend a little bit harder in just that one spot, which again helps you dial it in. Usually, once you get those dialed in, you get those adjusted where you got 90 all the way down, they're set, and you leave. Now, the one caveat to that is the reason I prefer them to be set to the minimum is they are mechanical. They're just held in place by one little bolt. They do move. If they're at the minimum, they can't move anymore because they're at the minimum. They can't go any further. They're like mechanical stops. If you have them in the middle, over time, they will move around. So something else to keep an eye on is, and again, we can go up and look at them later, is those wedges and those punch holes because they will move on. American, European. Now, on the Delem controllers, you guys, I'm sure most of you do steel, stainless, aluminum. Do you guys do any grade 80s or any kind of weird materials? Okay. There is an area on that controller to add specific material types. Anyway, the reason I bring this up, so there's a customer down south of St. Louis that they bought a 660 ton by 25 foot press for one part. This is one part. They used to have mechanic. They didn't, which I don't even want to think about bending this material on a mechanical. It had to. Well, they really bent. It was terrifying. That's why they got rid of the mechanical and they bought this machine. I can't remember what the material was called, but it had a tensile strength that was 10 times what stainless steel is. So, the installed machine, the very first part they want to bend is this part. So, okay. So I go and I look at all the material details. Tensile strength, elongation, blah, 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 etc. for this material. Look at the numbers, and I can't go look it up on a different webpage. Look up 3 different places. The numbers are right. So what they want to bend is 1/4 inch thick material by 18 foot. It has to be done on a 5 inch, the biggest V die they have, which is 5 inches. Now, normally 1/4 inch material, mild steel, gets bent on a 2 inch V die, right? 8 times 12 thickness, 1/4 inch, 8 times. I had to do it on the 5 inch, and I had 6 inch V die. What was the biggest one I had? It was 18 feet, it's just 1/4 inch thick steel, right? 500 some odd tons is what I take to bend that part. 1/4 inch material, again, I mean, it was, the tensile strength on it was outstanding. So, got it all set up. I programmed it. Then I went way over there. Have at it. There it is. So, they wanted like a 130 degree bend on it. I can't remember exactly. It's something like that. And they can now start bending that part, and it bent it to damn near a 90. If I'm sitting there watching this $10,000 piece of steel thing, I'll start. It's sprung back that far, from damn near 90 to a 130. And it came out within a degree. Because I put those numbers in there correctly in the material data library. It came out within a degree, even though it was that weird material. So that library is there for you guys. If you do get some grade 80s, any kind of alloys in, get the numbers, put it in there, it will help you out immensely. Because let the software do what it does. There's a lot of brilliant people that design that software. It does a ton of math for you in the background that you don't have to do it. You program it, it figures it out for you. So use that controller for your advantage. Granted, if you're going to steel all day long, what's in there should be fun. But if you get into any alloys, use it. Did any of you guys use the rubber latex for not marking up material?
Yeah.
Okay. fun with that. There's nowhere to take into account for that what that material is going to do.
Yeah.
And maybe someday someone will come up with a controller that takes that into account, what kind of material you're using. Because you put and I don't know if any of you guys have used it or not, but a lot of times when you're bending parts, they'll have stainless or some kind of material that's going to be on the outside of equipment. They don't want tooling marks on it. So they cut down this, a urethane sheet, right? So that it won't mark up the sheet. Well, that's all fine and dandy, but that's going to change when, in theory, is your material thickness, but also when you're bending it, that rubber's going to compress as well. So keeping consistent parts using that is, I don't envy it. It can be done, sure. It's just not easy. It takes a lot of dialing it. Grain direction, I don't know if you guys have ever noticed it on your steel, stainless, whatever material. Years ago when I was in Cincinnati, they had a software called Adapt, where you could have varying thicknesses come through and the machine would take that into account and bend the same all the time. It was very expensive software. Johns Hopkins University was involved in developing the software. It was very expensive. But we had a customer that had bought the software and flew up and down and did not work. Couldn't keep consistent parts. So we had a sheet taken in there, a sheet of steel, that we knew where it came from. Because that's one thing. When I go to shop, I have no idea where you're getting your steel from. 10 years ago, a bunch of us come out of Russia and China, and it was horrible. I was getting calls all the time, probably 15 years ago. Machine's not accurate. Well, I go in, and I have 6,000 difference from one sheet to the next. The machine's accurate. Your steel's garbage.
Yeah.
So anyway, we had this customer that they were claiming, this expensive software that I paid for does not work. Okay, so me and my boss went in there. We had a sheet of steel brought in from our supplier. We then went and sheared it up. We sheared it in half. It's 5x10 or even 4. Sheared it in half. Then we sheared one half of that sheet this way. Then we sheared the other half this way. And we went and then bent all the one sheet. All came out within a quarter or within a fraction of a degree. We then bent the other sheet that was sheared the other way. All came out within a fraction of a degree. But between the two pieces, there was half a degree difference. And that was all just doing the grain of the material. Which at the time, there was no accounting for grain. It could account for thickness. Material thickness is one thing. Grain, you can't, there's no fighting. And I found more and more companies are starting to learn when they're lasering their parts or however they cut their parts out, they're trying to keep them all the same direction instead of cutting one part this way and one part this way because they've slowly learned over time that you're dealing with the grain of that material. And it does make a difference.
It does.
It depends on how accurate your parts are. If you're making parts for a shed, half a degree here and there doesn't matter. If you're making them for NASA, well, that's a whole different story. So that's one thing. Again, and this all goes back to you guys seeing what you're dealing with. And if you see that problem, going back to your engineers or your boss or whoever and say, look, there's a better way to do this to make, number one, my job easier, but also we have more consistent parts. Which, at the end of the day, as a press brake guy, that's all you want. You want to walk up there, program your part, bend a part, make a correction, and make 90-degree bends or whatever all day long. You want it to stay the same. You don't want to fight it. Well, part of that process is, before the parts even get to you, is that process. Because usually, unless you're doing PIMs at the end of it, you're usually the last person to handle that part until it's assembled. All right? It gets cut out, whatever, it's engineered. You bend it, then it goes to the customer or goes to manufacturing to be assembled, whatever. So there's a whole bunch of process that's happened before you even get the part in your hands. So paying attention to that process can make your job easier at the end of the day. So I kind of covered feet opening. You guys all have your magnets here. The nice thing about these, and assuming your machine has them, if you look on there, there's a chart. And this chart is designed to tell you, so when you walk up and there's a skid of parts at your machine, and you go, and hopefully you go, you grab your part and your caliper and you measure your part. Figure out how thick the material is. This chart's designed to tell you what VDI you should be using to bend that material. So over on the left-hand side, it shows you the decimal equivalents of different materials. It also shows a gauge. So if you're doing, say, 12 gauge material, all right, if you go over and find where the highlighted box is, that number represents how many tons per foot it's going to take to bend that part on a 7/8 opening VDI. So this all goes back to if you're getting the alarm on your machine, tells you force is greater than tool. I can't remember the exact alarm, but basically telling you there's too much tonnage for the tooling. That chart will tell you how many tons per foot it's going to take to bend that material. You can then figure out how wide your part is, figure out how many tons it's going to take, and whether or not you are over the tonnage of your tool. So that's what that chart is for. I know after you've been running for a while, I know a lot of operators, they just know this is this die. Well, just because that's what you were told doesn't necessarily mean that's true. That's what that chart is for. Now, granted, you can go smaller VDI, you can do smaller radius, smaller flange, whatever, but there's limits to it. I go into a lot of shops, especially like 10 gauge, 1/8 inch. I'll see them bending on much smaller VDIs than they should. Now, does that mean they're hurting anything? No, it's still within the tonnage limits of the tooling. Instead of running at 10 tons per foot, they're running at 25. Which, that's what you got to do. It's what you got to do. Because again, a lot of times you're stuck in a rock and a hard place, right? The engineer wants this flange on this thick material. Well, you need the parts made, so you go and you do it. Does that mean it's the safest thing to do? That's where this chart comes in handy. You can find out if you are actually going over the limits of your tooling, assuming you know what the rating of the tooling is. And again, most standard tooling is 30 tons per foot. Once you get into goosenecks, tools that have reliefs and acute tooling, then you're down to about 20 tons per foot. So if you're not using straight up and down punch and die, assume that your tooling is not 30 tons per foot. Assume it's less than. Always be conservative. Again, this all goes back to being safe, not blowing out tools. So, I guess we can go there. Bend allowance. And this varies wildly from shop to shop. Some shops are all inside dimensions on the shop floor. Some shops are outside dimensions. And some shops, like depending on the engineer that drew it, could be both. The software on your controllers does a very, very, very good job at calculating outside flange dimension. And I've seen more and more shops are going to outside dimensions. Outside dimensions are easier for the operator to measure. Trying to measure inside dimensions is because of the radius inside that corner, you can't really measure accurately. Outside dimension, you're going from this outside of the material to this end of the material. It's very easy for the operator to measure. Again, depending on the shop, depending on the engineer whoever drew the part, depends on how it comes out in the shop floor. Hopefully, more and more are doing outside dimensions to make your life that much easier. On these controllers, when you draw a part, which, again, it doesn't matter if you draw it or if you just write a program. You're going to get the same part at the end of the day. But on the new latest software, when you go and draw a part, one of your options is, do you want outside dimensions or inside dimensions? And that's up to you, however you want to program it, and how the actual drawing is handed to you. The one drawback to that is if you've got a print in your hand that, well, this dimension is outside dimension, this dimension is inside dimension. That's where it comes in handy on these controllers. If you write the program instead of draw it, depending on how the controller is set up, and again, I don't remember who's set up how, There's a software switch in there that when you write a program, that's either turned on or off for your bin alarms. I like to leave it turned on because I'd rather have it calculate that correction for me than I can get rid of it if I want to. Because I don't want to do any math. If I have my choice, I have no desire to do any math if I don't have to. That software will do all the math for me. And I can go and I can write a program that's even my prints all inside dimensions. Well, once I write that program and go into it, it's going to have a correction in there for my back gauge to give me that offset to give me my outside dimension. Well, if I don't want to use that, I can go zero that correction out, then I'm at inside dimensions. So that way the software is doing all the math for me. Now, if you go and draw it, and you have a combination of outside and inside dimensions, you're stuck. You either have to do the math yourself for the one bin, either you're all inside or all outside, and you draw it. There's no real way around it. So that's where knowing how to use that software and what it can do for you determines how you program. And again, it's all determined, it goes back to, all determined by the engineers that do the prints. So, and we can get into that and how you go about doing that once we get out on the controllers. I'm assuming all you guys know how to use calipers and again, I mean, a lot of this was more for truly press brake 101 guys that have never seen a press brake before. You guys have all seen a press brake. You know what a press brake is. So I don't know. Half of this I don't need to cover. You guys already know this. And how to develop bin sequence. Software does that for you. So I didn't even know. Do you guys have any questions? What time is it?
10 o'clock.
10? You guys have any questions? Before we take a short break. No questions? Right. But again, because I'm all with Mike, how he wants to go get through this and get up the controllers, because that's where all the learning happens. I can stand here and talk to you all day long. But until you get your hands on there and start actually programming it and figure it out for yourselves, that's where the learning happens. And I've been doing this a long time, and I found, because I used to, my training used to be, I would spend a whole lot of time training, going through all this and all that. I finally realized I go through the training fairly simply once, and then, okay, now you do it. Yes, that's how most press brake operators. That's how they learn. Yes. If you're running a press brake, you're a hands-on kind of guy to begin with. So that's when the learning happens. I can stand here and talk to you all day long, and I can push buttons for you all day long. Until you start pushing the buttons yourself, that's when you start to learn how to actually run the machine. So, you guys see anything else on here that you think I need to go over more in detail?
We at our shop we do a lot of ID measuring. And do you like that drawing software on the? Do you use that?
Yes.
You know, I mean,
I do.
We to this point we've only had our machine maybe 6 months, maybe a little longer.
Yeah.
But so far we almost have not used that.
The drawing
part of it.
Oh no, yes. I will. The drawing, and this is where, okay, so when I started with Cincinnati 20 plus years ago, I was promised back then, at my hiring interview, how easy it's going to be to draw parts on a controller.
Yeah.
No, it was a nightmare. You would spend half an hour trying to draw a part on that controller, where I can just write a program in 2 minutes.
Yeah.
And it has been a long, long struggle by press brake controller manufacturers to come up with a good method of drawing on the controller.
It seems pretty easy.
Well, that's the touch screen revolutionized everything.
Yeah.
So even when the Delem first got their touch screen, it was still garbage because they were trying to use their old format for the software that was all push buttons on a touch screen.
Oh yeah.
And the two don't. It was so eventually they they sat down with someone. I don't know who sat down with who.
Yeah.
But they rethought the whole thing. How to redesign this controller to work best as a touchscreen, not the old push buttons and all the selections. And over time, they've come up with it's brilliant.
Yeah.
I mean, I can, assuming it's not a terribly complicated part, I can draw a part faster than I can write a program, or as fast.
Oh yeah.
And that's never, until recently, that wasn't possible. it always took longer to draw than it did to write a program.
Because I want to, maybe not here, but I want to start using that drawing.
Mhm.
We'll have,
Okay, that's
we'll
fine.
have a piece with all different Z bends in it.
Mhm.
And I thought, just let the computer do that.
Yep.
Tell us how big
Yes.
the part should be.
Yes.
You know what I mean?
Right. That's the beauty of drawing. There's a few beauties to drawing a part. Number one, you have a graphical representation of that
Yeah.
part on the machine. So if you have an operator who didn't write that program, but he needs to make that part, well, how do I put the part in the machine? Well, so I stick it in there, do the first bend. It's going to show me how to put that part and orient in the machine for the second bend. This is going to show where that bend is and how it's actually in the machine. If you draw, if you try to program, well, the operator the guy running this part that didn't write the program has no idea, unless he sat down and figured out the bend sequence up here. The other thing is it tells you what your blank length is, so it's going to tell you what size your blank should be to make that part. Within, it's not. I found over time it's not perfect, but it will get you very, very close.
Does it help you know which bend is first? And
Yeah, it figures it out for you.
See, that's where
Yes.
can change them.
Yeah, and then you can modify them how you want to.
Yeah.
Yes. And we can get into all that after under control. Yes. But, drawing, again, it's taken me a long time to come around to it. Because when I started, you programmed everything. There was no drawing, there was no graphics, there was no touch screen. You went, I want a 90-degree bend, and I want a 2-inch flange, and you just put the numbers in. Now, I'm kind of almost ashamed to say it, I always prefer drawing.
Yeah.
Because it's that easy, and at the end, I have a blank length, I have a graphical visualization of that part on the screen, so again, if I'm not the person running that part the next time, whoever is knows how that program runs, what the bend sequence is, graphically. They're going to have to figure it out. So yeah, I'm a big fan of the drawing on these controllers with this software, just because when you come back to it 6 months later, even if you're even if you were a program, 6 months later, you're not going to remember what the exact bend sequence was.
Right. We ran into that recently. When we had a part, they said, you know that pan you made? We need another one.
Uh-huh.
And we're like, oh crap.
Uh-huh.
So we have to remember the
Uh-huh.
allowances and
Yeah.
which order we did it in.
Exactly. So, but if right now, had you drawn that part,
Yeah.
then it would all be right there on the screen.
Yeah.
So yeah, as I say, I'm slowly becoming a converted over to the drawing, just because now, mind you, on these controllers, I don't think any of you have a 69. There's not many 69s out there. These controllers are 2D controllers, meaning you cannot draw a box. You can draw these two bends for your box, and you can draw these two bends for your box, but you cannot draw it all as one item. On these controllers, there is a way to connect this program with this program. So it will run bend 1, bend 2, then bend 3, then bend 4, then bend 1, then 2, 3, 4. You can't connect programs together so that they run in order. So that is the one, I don't know. Typically, if I'm making a box, I just write a program. Because, again, you can't really draw a box on the controller. And even if you did draw the two different things, or two different sides and two different sides, it's not going to show you how that box goes when you go to form it. Because when you go to bend the third bend, it's not going to show these two legs already sticking up. So there's not really an advantage to drawing a box per se on this controller. Can you do it? Sure. That's more up to however you guys want to do it. So that's the one drawback. They do make a 3D version of this controller. I don't know what the price variance is. I'm sure it's a lot. But on that one, you can do boxes, and it'll show you all 3 different sides, 4 different sides. But I don't think any of you guys have a 69. I think you guys are all 58s and 66. So, anything else we can think of before we get out of this hot ass room?